All right. So, all right. Still not. There's nothing coming out of this mic. All right. Oh, okay. I see why. All right. Okay, that works. Well, I do have to apologize. I really tried to get everything graded over the weekend, but I could not. I mean, I really pushed as much as I could. Um, so I'll still be working on it. So the streaming is already on. So what we'll do today is kind of continue our topic. Um, Today is the due date of the swap homework assignment. So one thing I can do today is to kind of share with you my solution to that homework assignment. I hope most of you have a chance to actually get it done. So we'll go ahead and take a look at that particular program. Question? Huh? It's already closed at this time, yes. So I make sure that the assignment is closed by the time the lecture starts so that people do not miss the lecture to get the homework assignment done. So we'll go start with that. Okay. There we go. All right. So that one, the thing is called function calls. And if you look at one of the questions, it has the C code. So we're going to go with the C code and just gradually work on the assembly code. Yep.
Just a quick thing.
Yeah.
I noticed one of the questions was worth 0 points.
Yes. So that was my mistake, but you can still tell whether you get it right or not, except, it's worth 0 points. But thank you for pointing that out. So this is the swap subroutine, and that's the main function. So what I'll do today is I'm just going to implement this entire thing from scratch. Okay. So you guys still can refer back to the question if you want to understand the concepts, because as you go through this particular lab, it's bringing you basically through all the topics that you need to understand in order to get it done. Okay. So we'll start with the assembly code for main first, because you cannot really test the subroutine without main. So we'll go ahead and start with main. All right. So we'll start with main, which is at the beginning of the program. The first thing I would do is just to give it a no op. So now by by this time, it's a good habit to start with no op, because we probably will want to run this through the trace analyzer, which means we have to use the command line version of Logisim to run it. So no op is good. LDID with 0 is optional, but I just do it as a habit, just to make sure that the stack pointer is initialized to something. And then we have main. This label is not needed because nobody is calling main. Okay, I put this label here just so that visually we can see that this is the beginning of the main function, but it is really not needed. If you do not define the label main, nobody is gonna miss it. All right, so the first thing we need to do in main is to reserve 2 bytes for x and y. I think in the question I reserve y first and then I reserve x. So we do a decrement D to reserve for local variable y, decrement D again to reserve for local variable x. I think that is the case. Is that right? Okay. So at this point, it might be handy to have a symbolic name to refer to local variables x and y in main. So the usual way that I do that is to look at what is on the stack. So on the stack right now, we have local variable y at a higher location. Then we have local variable x that is pointed to by the stack pointer at this point. Okay. So if this is the picture on the stack, then I define x as a label to be 0 because local variable x is 0 bytes away from where the stack pointer is pointing to. Local variable y, on the other hand, is 1 byte past local variable x, which means it is 1 byte on top of or above where the stack pointer is pointing to. Okay, and with these label definitions already done, then we can go ahead and initialize the local variables x and y. So x is getting a value of 3. I know x is 0 as a label, but if you use a more general way to do this, which is LDIA with the name of the label and then add AD. So at this point, A is going to be the address of x. And then once you have that, you need another variable to store the constant on the right-hand side of the assignment. So you have a LDI, let's say B with 3 this time. So B is now 3. So an ST instruction is going to store to the 3 to where register A is pointing to. But register A is the address of x. So if you want to look at the full account of what this is doing, this is what it's doing, okay? Which is a super fancy way of saying, oh, x as a local variable is getting a value of 3. Because %x is the address of x, so when you dereference the address of x, you just get x back. So we're actually storing a value of 3, which is in register B, to local variable x. Are we doing okay so far with the comments, not only the instructions, but also the comments of this program? We're good? Okay. So to initialize y, it's about the same thing. LDI AY, add AD, LDI B with 7 this time, STAB, just like last time, except this time y is going to get the value of 7. Now, main was given to you already, so you don't have to worry about this sort of thing. But if you're writing a subroutine or if you have to write main, it's not a bad idea to test your program occasionally. Like right now, if I put a halt instruction as my very next instruction, which means I'm not even bothering with calling swap. I'm just saying, okay, I got everything initialized. I'm not even balancing the stack pointer. I just want to know whether this works, okay? You can do that, okay? Now this will even work in the GUI of LogicSim because you can actually just look at the registers. You can look at register D and see where it's pointing to. It should be pointing to the location FE in hexadecimal. You can look at the content in memory. What is in FF? It should be storing 07 in location FF. It should be storing 03 at location FE. So it really helps to kind of write a simple program to make sure that this way of accessing local variables does work. Okay? Then you can kind of proceed, after you double check and verify everything is the way it should be. Okay. So assuming everything is good, we can now move on and we're going to call swap. So the way we call swap is we have to push the address of y first. Okay, now I'll just pretend that I did not know where the address of y is because it's already in register A at this point. I could have just pushed register A on the stack. But assuming that I don't want to keep track of how we use registers across statements in C and C++, I can always be just a little bit redundant and recalculate it. Is that okay? So at this point, A is the address of y, and we want to push it on the stack, which is decrement D and then stda. So now we have pushed the address of y on the stack. Now it's time to compute the address of x. When we compute the address of x, it is not just x anymore, because x as a label is assuming that we do not have anything else pushed on stack, which means x is the last thing that we have allocated on the stack. But right now the stack has one extra item, which is the second argument to call swap that is also on the stack right now. So if you want to visualize what the stack looks like at this point, that at the highest location we have y, the next location lower is x, and then the next location lower is the address of y. And the address of y is the one that is pointed to by the stack pointer. I'm just borrowing the square bracket notation to indicate that that is what the stack pointer is pointing to. So if the stack pointer is not pointing to x anymore, then you should not use just x here, but x1 plus, okay? So we use 1 plus to adjust, for that one extra byte that is now on the stack because we just pushed the address of y on the stack. Is that okay? Now you can also say, why don't we just collapse all of this to 1? Because in this case, your code has to work regardless of how local variables are arranged in main. So if I want to give myself more local variables, your code should still work. Does that make sense? The subroutine that you were writing should work assuming the parameters are pushed on the stack correctly, regardless of how things are organized in the caller. Does it make sense? Okay? Because when I was looking through or listening into how some people get this assignment done, they were trying to use things that the swap subroutine is not supposed to know, like where to find x and also directly where to find y. I mean, yeah, so that won't work. Okay, so now we add AD. So once again, A is now the address of local variable x. Push it on the stack. So now we have x also pushed on the stack. So right now, what do we have on the stack? You have, okay, so let's take a look at the stack at this point. I can take a snapshot, okay? So we can say, what is at location FF? That's local variable y, which has a value of 0.7, okay? What is the 1 byte below that? That's local variable x, which was initialized to 0.3. And then what is 1 below that? This is the address of y. And what is the address of y? Is FF. But what is the location? FD has 0xFF. And then 1 byte below that would be the address of x. It is at location FC, but it has the address of x, which is 0xFE. So if I were to put a halt instruction here with setting up everything, but without calling swap, this is what I should see on the stack. Is that okay? So you can go back to the code that is already in the lab and just move the halt instruction along from one location to another location, just so that you can see how the stack looks like at different points of time when the program executes. Okay, you can also use the trace analyzer. Okay, you can use the trace analyzer. Make the swap subroutine do absolutely nothing. Just put a halt instruction in the swap subroutine. Use the trace analyzer and find out what happens on the stack, what happens to the stack pointer, and so on. Okay, but every time you're writing something onto the stack, you need to know what you're writing. What is the context? What is that thing doing on the stack? Yes?
Yeah. And so how you wrote those things out, those are, the top line is the first thing that's in the stack, so it's upside down?
So this is location FF, location FE, location FD, location FC.
Right, so if it was an actual image of the stack, that would be upside down?
It would be an upside down stack, yes.
Just
So the end that is growing is down.
Yeah.
The base of the stack is actually all the way up. Which is usually how I visualize the stack in class. Yep.
Do you also have a return address somewhere?
Not yet.
Okay.
Up to this point, I have not pushed the return address. I have pushed the 2 arguments, right? Okay. So the next thing we need to do is to push the return address. So we already know how to do that, and it has to follow a kind of prescribed, sequence, because we like to copy and paste things in this case. So decrement D has to go first, and then we have the LDI A.5 plus. Now, if you do the decrement D after the LDI instruction, you just have to say .6 plus instead of .5 plus, because we have 1 extra byte of opcode in between the LDI instruction and where it is to return to. Okay, and then we have a ST instruction. Okay, this is the actual push. So we are pushing the return address at this point. And then we have a JMPI instruction to the subroutine that we are calling, which is swap in this case. And then when swap is returning, it's returning to line 39. We have 2 things on the stack right now. Those are the arguments. So we need to increment D twice to deallocate the two arguments. Okay, so this comment here applies to both line 39 and line 40. So at this point, we have two more things on the stack because we still have X and Y on the stack. When you look at the C code, there's nothing we need to do at this point, so it's time to deallocate those two as well. So this increment D is going to deallocate X, and this increment D is going to deallocate Y. And now we can actually have the halt instruction because main is done. So at this point, okay, assuming swap is not erroneous, at least in terms of how it uses the stack, at this point D should be back to 0 because we have deallocated everything that we allocated for main. Are we doing okay so far with this? Yep.
Can you count the 5 bytes again?
Say it again.
Can you count the 5 bytes?
Count the 5 bytes? Yeah. Sure. There are 4 bytes at this point, okay? Because, okay, let me copy and paste this. Copy and paste. So right before the JMPI to swap, on the stack, we would have FB, 0FB, storing the return address. Now, I'm not, I'm not going to count bytes myself to figure out what it is, but that's going to be the address of the JMPI instruction. The increment D instruction, sorry.
I meant the calculation for how you find the return address with the LDIA.5 plus.
Oh, how we calculate this one?
Yeah.
The dot is the address of the LDI instruction itself. So the dot is always the beginning address of whatever is on that line, the instruction. So in this case, the dot is right here. So the dot is the address of the first byte of the LDI instruction. LDI has 2 bytes. So the 5 is referring to the increment D instruction. How far is the increment D instruction on line 44 compared to the address of the LDI instruction on line 36? That's 5. Because we got 0, 1, 2, 3, 4, and that's 5. Yep.
I think you may have already said something about this, but what's the advantage of using that instead of like a label?
Because now I don't have to worry about using the wrong label.
Isn't that a different label than like any other?
Huh?
Like,
This is not a label. You can copy and paste this.
I know, but how would you screw up on like return like maybe I just don't know, but
if you have multiple subroutine calls, then you have multiple return addresses represented by labels. So if you copy and paste the code, you change where it's jumping to, but you if you forget to change the return address label, then it'll return to the wrong place.
Okay, that makes sense.
Yeah, so this way, I never will go back to the wrong place. So any more questions about main? Because main is pretty much done. Are we good so far? Okay, all right. All right, so in the subroutine, okay, so now we're moving on to swap as a subroutine. So in swap as a subroutine, what can it possibly know? What can it assume and say, yes, I can count on this, okay? Assuming the caller is working correctly, what can it count on? Well, it can count on 3 things on the stack. Yep, it can count on the 2 parameters. PTR2 has the higher address because it's the second parameter. PTR1 is the first parameter, so it's right below PTR2. And it can also rely on the caller pushing the return address on the stack, and the stack pointer is pointing to the very last thing that was pushed. So the stack pointer is pointing to the return address. This is all swap can rely on. It cannot use X, cannot use Y, cannot use things that only main is supposed to know. We good so far? Okay. So now the question is, well, what do we do about this? The first thing we need to do is to allocate also for the local variable t, because I want to stay true to the original C code. So I'm not going to use other tricks like pushing stuff on the stack and popping in a reverse order, that sort of thing. You can do that too, if you do not have a C code to go with first. Okay, so we're going to decrement D, Okay, this is going to reserve byte for local variable t. So after this, okay, if you want to know what the stack should look like, it's going to look like this. So we'll have, t also allocated, but now d is pointing to t. So that means return address is 1 byte on top of t, ptr1 is 2 bytes on top of where d points to, and ptr2 is now 3 bytes above where d is pointing to. Are we still doing okay so far with the picture of how the bytes are organized on the stack? Okay. What about the other bytes that are also on the stack? In other words, what about, because that would account for, okay, let me show you which bytes we are talking about. So looking at the earlier map, okay, come on, okay, scroll. So talking about all the other bytes, okay, so basically the subroutine only should know and count on these bytes on the stack. The subroutine at this point should have no concept of these 2 bytes on the stack. Okay, not directly, okay, but they can access those 2 bytes indirectly using the parameters. Okay, so getting back here. All right, so now it is kind of handy to use symbolic names again, because I like to use symbolic names so that I don't have to remember where's t, where's point ptr1, and where's ptr2. So we're going to use some symbolic names here. T is going to define to 0. Return address is going to be defined to t1 plus, because it is 1 byte above the local variable. So keep in mind that any local variable, such as t in this case, can only be allocated by the subroutine itself. The caller has no idea of how many local variables a subroutine needs, right? Because in C and C++, you already know that you can have one subroutine defined in one file, compiled to one object code file, have another subroutine, the caller, defined in another file, okay? And the caller can call the callee without even knowing the source code of the callee. So without knowing the source code of the callee, how can the caller possibly know how many bytes to allocate for the local variables? It does not, okay? So it's the subroutine itself that is responsible to allocate for the local variable. And then on top of this, we have ptr1, which is 1 byte above the return address. And then we have ptr2, which is 1 byte above ptr1 as a parameter. So those are the 4 labels, for each item that is on the stack. Return address is for the most part useless, okay? It is only here so that we can account for everything, okay? We just give a name to everything on the stack. But T, ptr1, ptr2 are definitely useful because those are the names that we refer to in C code. All right, so moving on. So the first line of C code says, we have to get to what ptr1 is pointing to, get that byte, and then store that byte into my local variable t, okay? So as you would probably imagine, okay, this is going to be some pattern that we have seen already. LDA ptr1, okay? So at this point, what is in A? A is literally really just a very small number at this point, because if you look at how we define the labels, T is 0, return address is 1, ptr1 is actually 2. Every time we refer to the label name ptr2, the assembler says, oh, you mean 2. So it's literally just doing that, which is not the address of the parameter at all, but it is the displacement of where you can find ptr1 relative to where the stack pointer is pointing to. So that means if once I add the stack pointer to A is now officially the address of ptr1, just like how we access the local variables in main. Okay. Well, that's useful, but that's not exactly what I want, okay? So the first thing I need to do is to do a LDAA. So once I have done one dereference, then we have ptr1, because I can make that a little bit more spelled out, okay? Because A originally had, on line 66, A is the address of ptr1, and the LDAA instruction is really just dereferencing register A and then put whatever it's pointing to, whatever A is pointing to, back into A. Is that okay? So if someone in his or her mind, in that person's mind, in their mind, okay, to be politically correct, in their mind is thinking, but what is LD doing? Okay, how am I supposed to answer the question? What do you think? If I'm the person sitting on this side and you're the person standing on this side, and I ask at this point, I don't understand how LD works. Well, how would you answer that question?
It loads like it's load dereference, right?
Is load dereference.
So it loads the dereferenced value of what the address says.
Yep. So what resources do we have to answer that question? Let me ask you in a slightly more specific. So we look at the opcode table first, right? So we go to the opcode table, we look up what LD, how LD is explained, okay? It says LD XY in parentheses is X gets star Y, okay? We dereference Y to get whatever Y is pointing to into register A, okay? But that really is just a description. How do I know that the processor can actually do that? We look at the ROM, right? So we look at the ROM, okay, okay, there's a shortcut to do it. You hand assemble, one opcode, okay, LDA in parentheses B, okay. Pick two registers. You hand assemble it, you inject that into RAM, or you can directly inject the opcode into the microcode pointer, okay, and then it will point to that location. Then you analyze, what components are active, what components are inactive, how the multiplexers and demultiplexers are, are paving, pathways between the components, and that is how someone can understand how an instruction is implemented. How does it dereference, and how does it get the content that is being dereferenced back into the register, the first register that we specify in the instruction. That is the process, okay, to make sure that we have a thorough understanding of how the instructions operate in the processor architecture. So are we doing okay so far? Yep, okay. So it's easier to do it in Logisim, but without Logisim, you can still do it, looking at the bit pattern, but it just gets a little bit more hairy, if you do not have Logisim to help you, because Logisim automatically breaks down all the bits already into what they should be. Okay, so now we go like, we have PTR1, but according to the C code, that is also not what we really want, okay? We're on the way to get what we want, because what we want is whatever PTR1 is pointing to. So now we have A is basically whatever PTR1 is pointing to. It is the byte in memory that PTR1 is pointing to. So what do I do with that? I'm supposed to store that into T, local variable T. Now you could, okay, doing this is fine, okay? It's a very shorthand way of doing it, but that's exploiting the fact that T is where the stack pointer is pointing to. If you have multiple local variables, then you kind of have to keep track in your mind which one is the lowest one and D is pointing to it. So instead of using my brain juice to memorize all of that stuff, I'll just pull a template and go like, okay, we need to find out where that thing is. So LDIA with T this time. Oh, cannot use A, we have to use B. So load add BD, okay, so at this point B should be the address of T, and that's all we need, because we are going to store to whatever B is pointing to the value of A. So this is going to do something along this line, which is kind of what the C code is saying. Are we good so far? Yes? Okay. Now, if you're writing this program and you're not really sure whether your code is working, 100% or not, it is not a bad idea to test your program, just kind of every, like 6 or 7 lines in the assembly code, put a hold instruction, check out everything, make sure it works. Yep.
Is that just good practice? Because isn't T 0?
T is 0, but that's only because we only got one local variable here, so it has to be being pointed to by the stack pointer. But if you have multiple local variables, then you have to keep track in your mind which one is the lowest one to use this trick. So I'm just using the approach of, this cannot go wrong. Okay, it might consume a few more instructions, but it cannot be wrong.
Because you're using the label.
And that's the whole reason of using the label, so that I don't have to maintain that mental map of where everything is on the stack all the time. Because once I have the labels defined up here, I just have to know how to make use of those labels. And I don't have to worry about, okay, which one is a local variable and which one is a parameter? Makes no difference. Is that okay? Yeah, okay. So we move on. The second line looks a little bit, kind of hairy because we have two dereference of pointers. But if you know how to dereference one, okay, dereferencing the other one is not too hard. So we deal with ptr2 first, okay. Add ad, ldaa, ldaa. Now, if you're writing this, I would suggest that you actually comment on each line so that you know what is in A after each line, okay? Because that's just good practice to help you kind of strengthen your understanding of how C code gets things done and how the assembly code gets the same thing done. Okay, on the other side, we got ptr1, so we got that. Okay. So, oops, cannot use register A. This time we have to use register B. So B is now the address of ptr1. Okay. Well, kind of what I need, but not what I actually needed. So we need a LD instruction, LDBB, BB. So the B is now the dereferenced pointer, which is basically just, it's really just pointer 1. But we are not going to store into pointer 1. We want to store to where pointer 1 is pointing to, which means we need one more dereference. But we are not going to use LD for this particular dereference because it depends on the purpose of the dereference. If you're reading what you're dereferencing, you use LD. If you're writing to where what you're dereferencing, you use ST. So that's that's how we use those two instructions. One is for storing, one is for reading. So since we're storing to whatever B is pointing to, whatever the right-hand side is. The right-hand side is already in register A. So this ends up doing whatever ptr1 is pointing to, is going to get whatever ptr2 is pointing to. And then we move on. The last one is to retrieve what is in T and then store it in whatever ptr2 is pointing to. Now, obviously, you guys can see that, it would be a good idea to keep ptr1 and ptr2 in some registers because we keep having to recompute those. So that's fine, okay? In the final exam, if you say, okay, I want to kind of shortcut the whole thing, because I remember this register still has blah, 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 that's okay. But in the class, I just want to use the most mechanical way of translating the C code because that cannot be wrong, okay? It can be tedious, it can be inefficient, but it cannot be wrong. So I'm going to do it the tedious way, okay? So we have LDI, A with T, add AD, and then do a LD instruction, AA, okay? So at this point, A is going to be the same as local variable T. On the other side, we got something that's very similar to something that we have done already. So we have LDR B, PTR2 this time, add BD, LDBB, and then STBA. Because register A has the right-hand side, register B has what we call the L value of the left-hand side of the assignment operation. So when you store A, which is the right-hand side value, to whatever B is pointing to, we have the whole thing done. Are we doing okay so far with this code? Okay. Because what I want you guys to be able to get out of this is to get a pattern, okay? Not really just to look at each instruction individually, but look at groups of instructions. Say, oh, this group of instruction always gets this done. This group of instruction always gets that done, and so on. Are we good so far? So at this point, I'm done with the actual statements in swap, but I'm not quite done yet as far as the subroutine is concerned, because in C and C++, you can just go like, oh, we're done, close curly braces, everything is good. But in assembly code, you gotta clean up stuff and return, explicitly. So the first thing we need to do is to increment d, because otherwise the stack pointer would still be pointing at local variable t. So if I use the return code without increment d first, then I will be using the value of t as the place I need to go back to. So your program most likely will go to a place that it's not supposed to. So in this case, it will go back to which location? Let's check. So t gets the value of whatever ptr1 is pointing to, and that turns out to be the address of x, which has a value of 3, right? So if I forget line 93, the increment instruction, the program will continue execution at location 3, which is an earlier point than what I should be at this point. So the execution of the code is going to look very confusing because it's not going back to where it's supposed to. Okay, so this increment d is very important. So let me comment why we do this. So it is to deallocate local variable t. So after that, then the stack pointer will go back and point to the return address, because remember the return address is 1 byte above the local variable t. So at that point, now since swap does not return a value, I can just use register A. Okay, increment D, and then we have a JMP register A. That's the return sequence. Are we doing okay so far with everything that is already on the projector?
The last increment D just deallocates the return address.
Yes. And that is by convention, okay? So by convention, the subroutine is the one that is deallocating the return address.
And then the caller would be
Yes, which is already done in when I wrote main. Are we good so far? Okay. So I have just done something that I try to preach you guys not to do, which is to write the entire program and then test it. And like, well, we'll cross the fingers and say, maybe it'll work. Okay, there's a likelihood that it will work. Okay, but when you're writing this, you really should be testing it like, write 7 or 8 instructions. Okay, implement 1 line in C code, stop. Okay, put a halt instruction, make sure it stops right at that point. Check out everything. Check out the stack pointer. Check out the content of stack. Make sure everything looks good before you move on. Okay. So we'll go ahead and give this a try. So we got Control C, and then go back and reopen. I closed all of the tabs over the weekend because I needed to do something else. So go back here, go to shared. And you can also make a copy of things that we have done in class. Like, unless I do something else, okay, this program is going to stay in place, for a while inside the assembler. So I can make a copy of the assembler, right after I get this code to work. Okay, so paste. And well, this program is just a little bit shorter than the previous one. That JMPB is not going to hurt anything because it's right after JMP-A, so it's not going to mess up anything, but I just don't want it to be there. Huh? I got one unknown mnemonic because I had a typo, ADD instead of add. How do you know you have ADD or attention deficit disorder? You spell ADD as AD. Okay, so we got everything. Good. So we'll download as CSV. Save the file as swap. There we go. And then we use a command line window here. Is that too small for most of you? That's what I use, when I'm actually doing coding myself. There we go. There we go. Okay, so we can now maybe just cheat a little bit. Okay, we can. Nope, not this one. We'll pick up this one. And then just change the file that I'm loading. Instead of a string copy, we're gonna change it to swap. There we go. Okay. All right, so that's a good sign, okay? Because if it doesn't get to the halt instruction, then it'll keep going, okay? Because that's the only thing that will stop the simulator in the command line mode is when we get to the halt instruction. So this is a good sign. At least we got to the halt instruction. And now the next question is, what does it look like? So for that, we're going to go back to here, and then we open the trace analyzer spreadsheet. Okay. And then we import, upload, swap dot, oh, no, it's log.tsv. There we go. And then we switch to analysis. Wait a long time for the computation to be done. Okay. All right, it's done. So if I am overconfident, what am I going to look for? I'm going to look for updates to location FF and location FE, because those two are supposed to be exchanged when it's all done. So we'll look at the beginning first. Okay, so we look at the beginning, and RAM write are in column C, so we can just kind of focus on column C at this point. And you can see how, oh, where's FF? Uh-oh. There we go. Okay, so we have FE getting a content of 0.3 to begin with, FF getting a content of 0.7 to begin with. So that's okay, that's correct. Okay, X is supposed to be 3, Y is supposed to be 7. And then we can ignore all of this, okay, and we just say, okay, did we end up exchanging those values? So now we can see FE is getting a value of 7, which was 3 to begin with. And we can see FF is getting a value of 0.3. It was 0.7 to begin with. So the swap operation did work correctly. And then the other thing, quick check that you can do is to see whether the stack pointer is balanced. In other words, when we are about to get out of the entire program, is register D the stack pointer going back to 0? Because it is supposed to go back to 0 when everything is done. So we can scroll down here and we can see the last update of the stack pointer. In fact, return it back to the value of 0, 0. So this is a super quick check, to see if the program works or not. Obviously, if the program does not work, there's a lot more analysis that you have to do. But between this tab, okay, between the analysis tab of the trace analyzer and the, well, I'm gonna promote. You can use the assemble tab. Okay, the assemble tab has a lot of information, which is great, but sometimes it has too much information, so it's kind of busy. You can hide some of these columns. Okay, once you make a copy of the spreadsheet, you can feel free to do whatever you want. Okay, so you can hide some of the columns that are of no use to you, but you can also go to source debug, which is really helpful. It's kind of clean, and at the same time, it shows you the address of each opcode in hexadecimal. So if you correspond column C of source and debug with column A of the analysis tab in the trace analyzer, that can really help you figure out what is going on with the program. Okay, but you do need to know what you expect the program to do first. Okay, so I would focus on, does it return correctly? Okay, am I setting up the parameters correctly? Am I accessing the parameters correctly? And so on. Okay, so is this helping? Yes? No? Maybe? Okay. Your next homework assignment is the recursive subroutine. We talked about recursion a little bit already, so that's kind of nothing too new to us. But this is something I want to kind of remind you is on this Friday, we have a hackathon on this campus from 9 to 9, so it's 9 a.m. to 9 p.m. If you want to sign up, there's a flyer as a bitmap, and go ahead and sign up. This is actually it's on Saturday. Thank you. So it's on Saturday from 9 to 9. Okay. So go ahead and sign up if you're interested. There's still room as far as I know. So it's going to be fun. It's good for beginners. It's good for people who already know how to program. It's just a good time to kind of hang out and do stuff. All right. So there's that. And then we go back here. And then we'll go to today's lab. Let me see what time we have. Yeah, we got about half an hour left. So at least I can start talking about it and give you some idea of how to get started with writing the Fibonacci subroutine. And then after that, we're going to have some fun with hack1.script. Teach a little bit of hacking. Okay, so we go to preview. And the first few questions are kind of just guiding you through the process, how our parameters pass from a caller to a subroutine. I mean, that should be pretty easy questions for you to answer. So now things get a little bit kind of hairy because this is what you're supposed to implement in this, in this lab. We're supposed to implement Fibonacci, and the way we're going to implement it is the recursive version, because there's a non-recursive version of Fibonacci as well. So the recursive version of Fibonacci can be done on a single line in C or C++, because I can use the ternary operator. I think we have explained the ternary operator a few times in this class. Yes? Maybe? No? How many people do not know the ternary operator?
I forgot it.
Okay. It's an if-then-else in a single expression. The first thing, which is to the left of the question mark, is the condition. So n is less than 2 is a condition. The condition can be true, can be false, right? If the condition is true, then the value of the entire expression would be the second part, which is the thing between the question mark and the colon. So that is called the then value. What if the condition is false? If the condition is false, then the third part of the ternary operator, which is everything to the right-hand side of the colon, would be the value of the expression. That's it. That's your ternary operator explained in a nutshell. Is that okay? So it's basically if, then, else. So it's basically just if, then, else as a conditional statement, but condensed into a single expression. Are we good so far? So according to this, what it means is if n is less than 2, I'm just returning n itself. If n is not less than 2, which means it's 2, 3, 4, and so on, I'm going to use the third expression, which is the recursive part. Now, the recursive part looks a little bit kind of hairy because there are 2 points of recursion. So we have to first call f again with n minus 1, figure out what it is. Then we have to call f of n minus 2, figure out what that is. Add those 2 together, the sum becomes the return value for this particular invocation of f. Okay? So you might want to use this code in C and C++. Just check it out with relatively small numbers just to find out how it gets the job done. Okay, you set up some breakpoints in GDB, stop at the entry point of f, see how the recursion goes in and comes back and go in again. So make sure you understand that process first. Okay, once you understand that process, then you can write your assembly code, because then you will have some idea of how to debug your assembly code. Is that okay? So if I were to write this code, okay, how would I write this code gradually? Because it looks simple, but it is still kind of complex. So the first thing I would do is really just to make sure that if I would first make sure I can just return n first. Okay, don't even have the condition here, just say return n. Okay, make sure that happens. Okay, that's not too difficult because the only thing you need to do to return n is you have to know how to access a parameter from within a subroutine. Okay, so that should be okay. Once you confirm that you can return n, which means you have a way to get to the value of n as a parameter, then you have to put in the conditional part. If n is less than 2, return n, otherwise return some kind of gibberish number. Okay, just make it up. 145, okay, whatever it is. Just so that you know how to evaluate a condition, return a true value, and then return a false value depending on whether the condition is true or false. So don't even go for the recursion yet, okay? Just substitute the recursive part with some kind of bogus value, okay, that is unlikely to happen on its own. Okay, so don't pick a small number like 1 or 2 or 3 because those things can happen on their own. Pick something that is totally kind of like not going to happen, like 47. Okay, are we good so far? Okay, so once you can double check and say if n is 3, okay, it's going to return 47. But if n is 1, it returns 1. If n is 0, it returns 0. But if n is, yeah, those are the only two that can return those things because it is unsigned. So don't worry about -1. If you pass ff as n, it should return 47 before the program is implemented correctly. Is that okay? Because ff is not less than 2. Are we good so far? Okay, so once you have that working, making sure that you can evaluate a condition and choose which expression to return, then you go for the recursive stuff. Okay, now there are 2 points of recursion. Don't worry about the double recursion part. Focus on one first. Okay, in other words, when you're writing the subroutine, just focus on returning f of n minus 1 without the other part. You can also substitute the other part with just a constant. So it's f of n minus 1 plus 3, for instance. Okay, so that would at least give you some idea of whether it works recursively or not. So if that part works, then you add the second point of recursion. Because it means that you know how to do recursion, it works correctly. Now you can add the second part. Are we good so far? Yeah? Yes? Now, in this class, did we ever talk about Johnny 5 and 7 of 9? No? Okay.
Something at 7 and 9. I think he mentioned something at 7 and 9, but
Okay. So, okay. So, in case we have forgotten, I can kind of remind you guys what that was about. Okay. So, let me start a new window. Okay. So the question is, okay, if you want to do something like this, okay, 12, okay, and this is going to return Johnny for 5, and then we'll have Ryan for 7. Jerry Ryan is the name of the actress who played 7 of 9. So Ryan is, okay, so if you really want the rest of the program, this is what it looks like. I think we might have talked about this program in this class, but I use it in cisp310 as well, so I cannot remember which class I used this example. Does that look familiar to you? No? Okay, well, that's fine. That means I can actually use it today. Okay, do we have any questions about how to implement Johnny or Ryan? No? Okay, they're just returning a single constant, right? So all you have to do is to LDI A with 5 for Johnny, 7 for Ryan, and do the usual return sequence, and you're done. Okay? So the question is, well, how do we implement 12? Because it has to use the return value of Johnny, but it also has to use the return value of Ryan. But register A is going to be overwritten, so that's a problem because when Johnny returns, it's good because register A will have the return value of Johnny. But then I have to call Ryan again. When I call Ryan, Ryan's going to overwrite register A with a 7, so I would have lost the return value from Johnny. Is that okay? All right. So how do we deal with that problem? So the way we solve that problem, okay, I'm not going to write the assembly code for Johnny or Ryan because those are relatively easy. So I'm going to start with 12, okay? So here's the entry point of subroutine 12, has no parameters, no local variables, nothing. So I do not need the labels for accessing parameters or local variables because there's none, okay? So now we can start with, okay, let's call Johnny first, okay? Johnny does not need any parameters either, so that's super duper easy, okay? We say decrement D, LDI, register A with .5 plus, store to where register D is pointing to, the value of A, which is pushing the return address, JMPI to the subroutine that we're calling, which is Johnny. And when it returns, right now, register A has the value that Johnny has just returned. Is that okay? And I know at some point I'm going to have decrement D again, LDI A, .5 plus, std_a. This time I'm going to call Ryan. And when that returns, register A is going to have the return value of calling Ryan. Now here's the problem, because by the time I get to line 12, sure, register A has the return value of Ryan, but what about the return value of Johnny? Would have lost it already, right? Okay. So that's not nice, okay? So one thing we can think about doing is to say, well, let's put it into another register. We can do a CPR pick register B, okay? Something like that. Well, you cannot count on this to work. Why? Because nobody says that Ryan has to preserve register B. Okay, any subroutine can overwrite all of the registers A, B, and C. Register D is a special thing because it's the stack pointer. So you cannot assume any subroutine to preserve a register that you, the caller, needs. Okay? So this may work sometimes, but you cannot count on it. So I would count this as an incorrect solution because you cannot count on it. So if we cannot do this, where am I supposed to stash the return value from Johnny? The stack, exactly. See, the stack is really useful in a lot of situations, okay? That's how I do it. I just push it on the stack. It is safe because, as a subroutine, okay, Ryan is not supposed to access anything that does not belong to Ryan. Now, Ryan has no parameters, has no local variables. Even if it did, okay, those are the things that is below the value that I have just pushed on the stack. So Ryan really should not be modifying anything that the caller has pushed on the stack like this. Is that okay? Now, if Ryan as a subroutine is implemented incorrectly or maliciously, then yes, it actually does have access to things that it's not supposed to have access to, but I'm making the assumption that Ryan is implemented correctly, so it should not be touching this byte at all. Is that okay? So then how do we utilize that byte that we have pushed on the stack? After Ryan returns, okay, which means the return value of Ryan is in register A, I still have that byte, which is the return value of Johnny, stored on the stack. So now is a good time to pop it, okay, to retrieve it from the stack. So we do an LD instruction. Don't put it into register A because register A is useful right now because it does have the value of Ryan, return value of Ryan. Put it into another register, say B or C. After I make use of it, I don't need it anymore, so I'm just popping that item. So at this point, what do I have? Register A still has the return value of Ryan. Register B, on the other hand, now has the return value of Johnny. Okay? And it's just a matter of adding those two. Because now it's the sum. Yep.
Don't we need to increment D twice?
No, just once. Because this sequence is the opposite of that sequence. This decrement is taken care of by the subroutine Ryan itself. because this is line 11 is for the return address, but remember the return address is deallocated by the called subroutine, not the caller. Yep. Okay, so it should have this done by now. So register A already has the return value, which is great. So now we can do a LDBD, okay, retrieve my own return address, increment D to deallocate my own return address, and then JMPB to continue execution in the caller, and everything is done. So you will need to know this trick to get the assignment done. And I'm not gonna spell out why. I think it should be fairly apparent. And I don't want to hear anyone complaining, but this example is not recursive. I cannot use this example. Recursive or not does not change the mechanism. It's exactly the same mechanism, whether it's recursive or not. I really hope by now, we have demystified recursion a little bit. Yes? Okay? Because, when I was, in a similar class like this, back in my college days, I had questions. It's like, how does recursion work? How can each invocation maintain its own parameters and local variables and stuff like that? Because the definition only has one, right? I mean, there's only one definition. So as it turns out, I was not separating two important concepts. The two important concepts related to subroutine is, one is the definition. What do you mean by definition? This is a definition, okay, of a subroutine versus the invocation. What is an invocation? How do you visualize an invocation? You can only visualize an invocation using a debugger or the trace analyzer, because it has to do with what is on the stack at the time when the program runs. So the idea of recursion is you don't have one definition, but you can have any number of invocations active at the same time. So is that helping or not? Did I ever demonstrate how to use GDB to visualize recursion in this class? Nope. Okay, let me check the time. We got plenty of time. We can do that. Okay. So let's see. I'm going to use your homework assignment as an example. Okay, just so that you now can have that technique to also help debug your own programs. So I'm going to implement Fibonacci. So we have un8 underscore t, f of un underscore t. We need to pound include something first. Pound include stdint.h. This is a good trick, you should probably remember and use it in your other classes as well, is to actually name the width of all the integers that you need to use. Okay, just don't use just int, okay, but also say how wide of an int do I need? 32-bit, 64-bit, 16-bit, okay. All right, so in this case, I'm just trying to stay close to the original code. So this is n, okay, and in here, I'm gonna say, do you guys want to use the ternary operator or the equivalence in statements? Ternary? Yeah. Okay. Okay, how many people want the statements? No one. Okay. Okay, so if n is less than 2, we return n. Otherwise, we return f of n minus 1 plus f of n minus 2. Okay, that's it. And then in main, now main is the only one that I use just regular int because that is what the compiler expects. So if I use the wrong width of int, the compiler is going to bark at me and go like, no, int has to be this width. So I'm not going to deal with it. In order for a C compiler to actually compile code that calls the subroutine, I have to store it somewhere. So I need x here. X is f of, what do you guys want? I mean, 0 or 1 is not going to be a whole lot of fun because there's no recursion. So you have to start with 2 to see some recursion. So let's start with 2. And that's it. Okay. Okay. GDB fib. And we'll put a breakpoint on line 4, which is the only line of the subroutine. Okay. On the program. So this is the first time we are calling Fibonacci. So this is called when n has a value of 2 right here, and we're on this line, which means we're going to call again, with n minus 1 being 1, and then we'll call it again with n minus 2, which means the parameter is going to be 0. Okay, but those two are called separately. Okay, so if I single step, this is going to be the second call to Fibonacci. So you cannot tell that this is another call to Fibonacci, even though you can tell that n was 2, now it is 1, but you have no idea whether I return from the previous one and then call fib again or what. So one really interesting and useful command that you can use is backtrace, BT. So this is what backtrace does. Okay, the dark blue stuff is not important, so we don't actually have to look at those. But what backtrace does is to show you what invocations are active right now, okay, up to this point. So we can see that in main is the first function called in the entire program. So in main, on line 10, we call f the first time, okay? But in f, on line 4, we call f again. So this is the second invocation. #0 or frame 0 is referring to the most recent frame that we have created on the stack. A frame is just a loose item or loose name to refer to all the parameters, the return address, and all the local variable related to one invocation. Okay, so we have frame 0, frame 1, and frame 2. So when we single step this time, it's going to return back to frame 1 because there's no need to recur. It's not going to do any more recursion because n is 1 already. Is that okay? So that means if I single step right now, okay, it goes to 5. It's still in the second. It's still in the second invocation of f. You can use BT to check that. We're at the end of the second invocation. If I single step again, it goes back to the first invocation because if you use BT, you can. Okay, so it returned back to the first invocation, and then it immediately called the second invocation of f of the first invocation of f, which is calling f again, but this time with n minus 2, and that's why we see n equals to 0 in this invocation. So your code is going to do logically the same thing, which means if you just want to look at the result of what is in RAM after the program runs, you would have missed certain things because locations are reused, in this case, on the stack. Okay, so the trace analyzer is a much better tool to help you debug Fibonacci compared to running in the GUI mode, because the GUI mode would not be able to capture all of these things that are in runtime. Are we good so far? Okay. So this is a good program to check out. Now, for those of you who want to be able to debug and be able to see the program execute a little bit better, you can first convert this code into the statement version, which is just saying if n is less than 2, then we do this, otherwise we do this. This is just returning n, and this is returning f of n minus 1 plus f of n minus 2. And if you're like me and do not really like to use returns inside a nested control structure, okay, to make it really spelled out, we can do a R here and another assignment of R here, and then return R. So this way we don't have any return inside a conditional statement. It will still work. I mean, the first version, before I changed to use a local variable R, the other version still works, okay? It's just a bad idea. I don't want you guys to kind of have the idea of, oh, it's okay to return from inside a control structure. Does anyone want to know why it's not a good idea? Yep. Yeah, go ahead. Hmm?
Oh, can you elaborate?
Why is it not a good idea to return inside a conditional statement? Why do I want to have a single point of return that is outside of all the control structures and all the way at the end of a subroutine?
Just make sure it makes it all the way through. I mean,
Yep. To make sure that any analysis of the control structure does not have to account for the fact that, oh, but I might actually get out of the subroutine way before we get to the end of the last line of the subroutine.
Well, I was going to say that.
Okay. Yeah, I know the previous version is used a lot in example programs, but in general, personally, I do not like, returns from inside a control structure. But is that okay? This program is better for tracing purposes because the conditional statement is on one line and the assignment statements are on other lines. So you can set up breakpoints, a lot more with finer control because the other program only got one line. So the only way you can set up a breakpoint is on that one single line, which doesn't help too much. This one, you can set up a breakpoint on the if, set up a breakpoint on the first assignment, set up a separate breakpoint on the second assignment. So it makes it easier to visualize the execution of the code. Yep.
So you know how you were saying you shouldn't return inside the conditional branches?
Uh-huh.
Does that carry over to assembly? Like, should we not LDIA within like the if branch, I guess? Or should you allocate a variable on the stack and then?
You don't have to do it, using this particular way. So you don't need a local variable. It's just one way to do it. Now, for those of you who really, really want to debug your program, and understand how the recursion works, you can even break up that line into two. So the idea of breaking up the computation of f of n minus 1 plus f of n minus 2 into two separate statements is now you can put a breakpoint on the first one and put a breakpoint on the second one. So it becomes really, really clear which one you're dealing with at which frame, when you're running this program. So for debugging and understanding recursion, this version is very verbose, okay? But at the same time, it gives you the ability to really check out how recursion works, okay? Which is kind of important because, you have to know what your assembly code is supposed to do first before you can debug it. And this will show you what the assembly, how the recursive calls are supposed to happen, who returns to whom, and then what else to do when at that point. Okay? So I'm giving you this version just for debugging purposes, or to understand how it works. And if you really want to get a better understanding of the recursion part, change 2 to 3 at least. Okay? Because if you change the 2 to 3, it would have multiple levels of recursion, at least with the left-hand side this time. So this will give you a better idea of, okay, f of which number, am I evaluating and in what order. Are we doing okay so far with this code? Okay. So with recursion, I think the most perceivable difficulty is actually how to write it, okay? In other words, if I say, okay, this is string compare, okay? This is the iterative version of string compare. Now turn it into a recursive version. That might be harder, okay? But if I give you the recursive version to begin with and just want to convert it into assembly code, that should not be as hard, especially now that we have the trace analyzer working really well to kind of give you an idea of what is pushed, what is stack, how do we change the stack pointer, and so on. Are there any questions about the Fibonacci program? Yep.
If you have enough invocations in recursion,
Say that one more time.
if you have enough invocations, like recursive invocations, can you
Uh-huh.
pull up your stack?
Yes, you can. The stack will run into the code, and then bad things will happen. Very bad things will happen.
Is there like a limit to that? Is it
You kind of have to evaluate it first. So if I go back to the assembler, okay, I can show you how how much stack space you have. Let's see. So if you go to the assembler and then you go to, there are two places where you can find that information, but I personally like assemble because it gives me really a lot of information that it can be useful. So if you go to the last instruction, in this case, it is the JMPA instruction. So the last location that we use in this case is 46 in hexadecimal, which is 4 times 16, 64 plus 6, which is 70 bytes. So the code for the program uses up 70 bytes, which leaves you with 256 minus 70 bytes for the stack. But you can run out, okay? So if you do not implement the condition correctly, or when you push, when you set up for the next invocation, you forgot to subtract 1 or then subtract 2, then you can end up with an infinite recursion, which will basically chew up the code, down to the program itself. It will chew up the code, in this direction, itself up, the code that is responsible for the infinite recursion. Then, depending on how you corrupt those locations, it would most likely, the fortunate thing is, any opcode that is not taken up is basically the same thing as halt. So that's kind of the good thing, because it will actually just stop if it steps on an invalid opcode. If you're so unfortunate that everything that you use to corrupt the stack are actual usable opcode, then it will just start to do crazy things. So that's why it's good to check the conditions first. Okay, you work on this step by step, make sure you can check the conditions, and also make sure that when you do the recursion, your n decreases, because then eventually it has to stop. Yep. But it's good for running up to, I cannot remember, f of a fairly large number, because every time you increase n by 1, it only deepens the stack by 1. How much space it would use, it will only deepen that by 1, but it will increase the execution time almost by doubling it. So in terms of how long it takes, by the time you get to f of 5 or f of 6, it might take a while, but you will still have a lot of stack space. So is that okay? All right. So we are just running out of time, perfect timing. I never really plan my time, unlike Professor Antos. Do you know how well he can plan his time? Did anyone take classes? Has anyone taken classes from Professor Antos? Damon Antos? No? He's about to retire. You guys have not experienced Professor Antos. He would, at the beginning of each class, he would write down the topics of what he's going to go over, and a time, down to the minute, of when that topic will be covered. I was evaluating him one time, and he was able to hit those minute marks. I barely have any idea of what I want to talk about on a per week basis, let alone per day, or per hour, or per minute. So anyway, this is going to be your new lab. Okay, you got a week to work on this. With this lab, it is not about spending a lot of time. It is how you spend the time. Okay, how you work on the program step by step, and how you debug the program. So in that process, I think you'll gain a better understanding of assembly language programming. And I'll be over the lab, so if you guys get into anything that you cannot explain, I'll be able to help you. So I'm gonna stop the recorder and get it. I will send the recorded video to you guys, because it's going to be unlisted for now, because the other class is still working on it.